Hi. In this problem, we are going to look at another question on triangle geometry. We have a triangle ABC where AB is equal to AC, and basically it's an isosceles triangle where I is the in center. D is a point on inside triangle ABC such that I, B, C, and D are concyclic. So I will be somewhere here, and there is a circle passing through these, and D is a point inside. D is a point inside the triangle such that it is concyclic with I, B, and C. So therefore, D, we can take D here, let's say. So let's say this point is D. Now, on the line AD, we join A and D. And E is a point on the line AD such that CE is parallel to BD. So BD also we have to join. And we extend AD. And CE is parallel to AD. CE is parallel to BD. So this is my D point. BD is this line. So I'll make a line parallel here. This will be my E. I will make this. This is my E point on AD such that CE is parallel to BD. Okay. Now let's say this AD line extended intersects the circle here at F. Let's say this point is F. We have to show that CD square is equal to BD into CE, right? So what we draw is we draw this BI and CI, BI and CI. Okay. I is the in center. So obviously these BI and CI are angle bisectors. Now we also join BF and CF. So BF is here. I have drawn it slightly incorrectly. BF will be here. F is this point. So these two are being joined. And CF is here. A line like this. Okay. Now we know that BD is parallel to CE. Now, if BD is parallel to CE, we know angle BDC. So you can mentally think of joining D and C as well. So you can join these two with a straight line. Angle BDC plus angle DCE should be 180 degree because these are parallel lines and these are interior angles on the same side of the transversal, right? Therefore, angle DCE is equal to 180 degree minus angle BDC. Angle DCE is 180 degree minus angle BDC, right? And now, because we know that F lies on circle circumscribing I, B, C, D. F lies on that circle. Therefore, angle 180 minus angle BDC. If you think about it, BDCF is a cyclic quadrilateral. So 180 minus BDC is equal to angle BFC. BDCF is also cyclic. Therefore, this result is true. Therefore, we get angle DCE is equal to angle BFC. Right? Okay. We also have, by the way, AB is equal to AC. So we need to remember that as well. So now we have angle CDE. Angle CDE. CDE is which angle? CDE is the same as angle CDF. Is the same as CDF. and is equal to angle CBF. Why? Why is CDF equal to CBF? Because CDBF are cyclic. Therefore, CDF is the angle by the arc CF, which is the same as the angle CBF, right? So these two angles are equal. Therefore, triangle BFC is similar to triangle DCE. It will be clearer if you just look at the circle diagram like this. Just focus on the circle here, and here we have B, here we have C, we have D somewhere here, I somewhere here, D, and F somewhere here, F here, and E somewhere here, E here. And if you look at this triangle, DCE, so B is here, and the triangle DCE, and I can join BC also, and the triangle BFC, BFC, BFC. So in this magnified figure, if you look at triangle BFC and triangle DCE, right, we know that CDF, this angle, is matching CBF, this angle, right? Okay. And we also know that this angle is equal to this angle. We have already shown that BDC and BFC are supplementary. So we have DCE equal to BFC, DCE equal to BFC. Oh yeah, we already have DCE, which is this angle, equal to BFC. So can you see this result is there? DCE is BFC, and we also have this result, right? So by AA similarity, we have these two triangles are similar, BFC and DCE, right? Go back through the arguments and you'll realize that this is similar. And if it is similar, we have DC by CE in triangle DCE should be equal to BF by FC by similarity. So this is my first result, right? Now I want to show that the sides AB and AC are tangent to the circle. I want to show that the sides AB and AC are tangent to the circle. How do I show that? Think about it. I have alternate segment theorem, right? In any circle, you have an alternate segment theorem. So suppose I have a circle like this, and suppose there is a point A here, and this is the point B, right? And I have I somewhere here, and I have C somewhere here, right? So if AB is a tangent, then this angle should be equal to the angle in the alternate segment. So should be equal to this angle, right? So I should have ABI is equal to ICB, right? Now angle ABI is equal to angle B by 2, but the triangle is isosceles. So angle B by 2 is equal to angle C by 2. And what is angle C by 2? Angle C by 2 is equal to angle ICB, right? Angle ICB is half of the angle because CI is an angle bisector. So therefore, we have shown that this angle made by the tangent and a chord is equal to the angle in the alternate segment. So by alternate segment theorem, AB must be tangent to this circle. And similarly, you can show that AC is also tangent, exactly same argument. AC is tangent also to the circle, right? So now we have AB and AC are tangents. Now we can also show that triangle ABD is similar to triangle AFB, and we can also show that triangle ACD. So first I'll make a claim here. Triangle ABD is similar to triangle AFB, and I also want to show triangle ACD is similar to triangle AFC. Let's just prove one of them. You can prove the other by the same argument. So why is it similar? Let's look at the triangles. So A is here. This is tangent B, A, and AD was a line like this. This was D, and this was F, and this was C. This was my C. AB and AC were tangents. So ABD and AFB, right? That is what I have to see. Okay, so we can say that both of them have a common angle, right? Angle A is common to ABD also and AFB also. So all I need to show is that is one more angle. One more angle is equal, right? So if you see this angle by the alternate segment theorem should be equal to this angle, right? This angle. Okay. Correct. Also, okay, I think I've made a mistake. I want to show triangle ABF and triangle BDF. This is similar. That is easy to show because if I make a BDF triangle, I have by alternate segment theorem, this angle ABD should be equal to angle BFD. This angle should be equal to this angle. And I already have BDF. This angle is same as this angle, and we have angle A is present here. Can we show basically BD by BF is equal to AB by AF? This is what I want to check. Can we show this? BD by BF equal to AB by AF. We already know BD from triangle BFC and CDE. BFC and CDE. We got this result. Okay. I will just rethink this. I need to show BD by BF is equal to AB by AF. and I want to look at this triangle ABD and AFB. AFB. Okay, so I have a common angle here in ABD and AFB. That is true. And okay, it is what I was doing earlier was correct, because this angle is the angle made by the tangent AB and BD, the line BD. BD is a chord. So alternate segment theorem says that it should be equal to this angle. So basically, angle A is common and angle ABD is equal to angle BFD by alternate segment theorem, because AB is a tangent. Because AB is tangent. So by now there are two common angles in the triangles that we are looking at, right? Okay, I was getting confused because my BFD is the same as basically angle BFA. BFD angle is the same as BFA angle. Therefore, in triangles ABD and triangle AFB, I have AA similarity now. AA similarity. I hope everybody is following. I got a bit confused because I thought we needed a different triangle, but by our alternate segment theorem and by one common angle, we are getting the similarity, which implies now that this is true. Now I think it is done. The ratio of the sides in these two similar triangles we have written like this. Now, if you think about it, BD by BF is equal to AB by AF, and BD by BF is equal to AB by AF, and AB is equal to AC, so it can be written as AC by AF. Okay, AC by AF, and now using this triangle, this similarity, you can prove the similarity of triangle ACD and triangle AFC in the exact same manner, just like we did this. It will also have a common angle. The common angle will be this, and it will also be done by alternate segment theorem. Okay, so you can prove this. You will get that AC by AF. From here, AC by AF will be equal to DC by CF. I will leave the proof of similarity to you. You can figure it out. AC by AF is equal to DC by CF by doing this similarity. And therefore, we can write this as DC by CF. So ultimately, what we are getting, taking the first and the fourth, we'll get BD by DC is equal to BF by FC. Taking the first and the fourth, we get BD by DC is equal to BF by FC. And now it is done because you already have proved this relation earlier, this relation. So we have DC by CE is equal to BF by FC. And now it is equal to BF by FC is equal to BD by DC. And therefore, taking the first and the third, we get DC square is equal to BD into CE. Basically, a little tricky. The question was a little tricky because you have to worry about multiple similar triangles. We have proved three similarities here. We got this similarity earlier. Then we got the similarity of ABD and ABF. And finally, ACD and AFC that you should figure out yourself. And if you do that, you will be able to solve this one. I hope you have understood the problem here. We'll bring more problems and more videos on this. There are a couple of more problems that at least I want to discuss, but that will be the subject of the next video. So ideally, what you should be doing is when we state the problem statement, you should give yourself 10-15 minutes and try to solve it yourself. If you try it yourself and then see the solution, it will benefit you far more. So hopefully you learned something from this video, and see you next time.